Hi everyone, welcome to this video which is the TGC Derived Grade Exam 2024 for Level 2 Chemistry, and we're going to do the Structure and Bonding exam, and this is question 1. I can get the page open. There we go. Alright, so the first question in this year's exam is a question about Lewis structures, shapes, bond angles and polarity. Pretty standard question. Right, let's start with the Lewis structures. OF2, my first job is to go to my periodic table and find the number of valence electrons for these. So O is 6 valence electrons and F is 7. And I'm going to put the O in the middle. Usually the single atoms go in the middle, but halogens for level 2 are always on the outside. So 2 Fs like that. I'm going to start with the Fs. 1, 2, 3, 4, 5, 6, 7, and 1 to make 8 for the F. 1, 2, 3, 4, 5, 6, 7, and 1. Just have a note of where I'm putting everything, just so that everything's in pairs and looks like it's between the two atoms that are sharing it, etc. And then oxygen, 1, 2, 3, 4, 5, 6. So everything's now got 8. This one has 4 areas of electron density around the central atom, 2 bonded and 2 not, so that is going to be bent or V-shaped. CS2 with a C in the middle and 2 S's. C has 4 valence electrons, S has 6. So I'm going to start with the S. With 6 valence electrons, they need 2, so I'm going to start with a double bond to get those 2. So 1, 2, 3, 4, 5, 6. And I'm going to do the same for this S, most likely situation. And then I'm going to check the C. It's got 4 of its own. And with the 2 it's sharing from each sulfur, that's 8. So everything's got 8. And this has got 2 areas of electron density, 1, 2. And so that is going to be linear. And our last one is CH2O. So I'm going to put my C in the middle and I'm going to spread my other 3 evenly around. C has 4, I've already worked that out back over here. H has 1 and O has 6, already worked that back out over here. So start from the outside as usual. H has 1 and needs 1. This H has 1 and needs 1. So the 2 hydrogens are sorted. Oxygen has 6, so it needs 2. So I'm going to do a double bond here. 2 from the carbon, 2 from the oxygen, and the other 4. And I'm just going to check that. I've got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 around the carbon, 2 and 2. That has got 3 areas of electron density around this central atom. So it is triangular planar. And that would be a little achieved mark there. Okay, so now we've got to justify why H2S has the same bond angle as CH4, but a different shape. So we have got bent and tetrahedral, so the shapes are named, but the bond angles aren't. So let's work out that first. So this one has got 1, 2, 3, 4 areas, so that's going to be 109.5. Doesn't matter if they're bonded or not. 1, 2, 3, 4, 109.5. All right, so let's just start with H2S. So I'm going to explain the shapes of each of them separately, and then I'm going to do the comparison at the end. There are other ways you can do it. This is just how I'm going to do it today. So I'm going to clearly say that I'm starting off talking about H2S, knowing that the examiners are not mind readers. So there are 4 areas of electron density around the central atom. The central atom is S. These areas occupy positions to minimize repulsion in a tetrahedral arrangement. Hedral arrangement with bond angles of 109.5 degrees. So that's an important link there. So we're linking the total areas of electron density to the parent shape or the arrangement and the bond angles. So don't try and do the bonded and non-bonding areas and link that there as well. It'll just not be clear if you do that. So what I'm going to do now is I'm going to actually switch to CH4 so I can do a direct comparison here. CH4 also has 4 areas of electron density around the central atom. I'm just going to abbreviate that in this video. These areas also occupy positions to minimize repulsion in a tetrahedral arrangement with bond angles of 109.5. So if I wanted to, just to make this clearer, I could say CH4 and H2S both have the same total areas of electron density around the central atom, therefore the same parent shape and bond angles. However, in H2S, 2 of those areas are bonded and 2 are non-bonding. So the shape is linear, whereas in CH4, all 4 areas are bonded. So the molecular shape is tetrahedral. The number of bonding and non-bonding areas is different. In H2S and CH4, therefore their molecular shapes are different. Okay, that's that one done. Let's look at number C, which I imagine is polarity. We're given 2 Lewis diagrams here, and we have to justify the polarity. We're not given those. So again, I'm just going to start with nitrogen. So I'm going to label what I'm talking about. The shape of N2 is linear. Always state the shape. The N triple bond to N is non-polar, as N and N have identical electronegativity. Therefore, as this is the only bond in the molecule, N2 is also a non-polar molecule. So it doesn't make sense in this one to talk about the central atom and dipoles being evenly distributed or symmetrically arranged. 1, because there's no central atom, and 2, because there's no dipoles. So if you started talking about dipoles for this one, then you don't understand polar bonds. There isn't a dipole because these electrons in here are evenly shared because these 2 have an identical electronegativity. So that's a bit of a trick one. I'll then talk about NH3. I will go, there are, oops, what happened? Something fell over. There are 3 polar bonds, as N is more electronegative than H. You should know that, but if you don't, you could just say they have different electronegativities. Therefore, bonding electrons are shared unevenly. and a bond dipole forms. Due to the shape, and I need to know this shape, so if you don't, you'd have to work that out. 3 areas bonded and 1 area non-bonded is a trigonal pyramid. So due to the shape of NH3 being a trigonal pyramid, the bond dipoles are asymmetrically arranged and therefore they do not cancel, making NH3 a polar molecule. Another way of saying that, you could say, instead of saying cancelling out, because the dipoles are asymmetrically arranged, the centres of positive and negative charge do not coincide. So that's another way of saying it. It's at the end of that question. Let me see. Nope. So we've got one more part to this question to do. All right, so here's a solubility one. That's a bit tricky. So we need to explain why ammonia gas, which we've just said is polar, is soluble in water, which we should know is polar, but nitrogen gas, which we've just said is non-polar, is insoluble. So our big idea in solubility is that substances are soluble in other substances if the bonds formed between the two separate substances are stronger and more favourable than the individual bonds. So what we can say is that NH3, a polar molecule, is soluble in water, a polar solvent, because the attractive forces between water and NH3 molecules are stronger / more favourable than the H2O forces and the NH3 forces. Put attractive forces, and in fact I can put with there. This means H2O and NH3 form sufficiently strong interactions to allow NH3 to be miscible in H2O. So I do need to mention the polarity somewhere there. However, as N2 is non-polar, the attractions between N2 and and water and H2O are insufficient to overcome either the N2 weak intermolecular forces or the H2O weak intermolecular forces. So N2 is insoluble in the polar solvent water. Yep, and I think that's probably good enough. This one's a bit tricky to draw a picture. So I probably wouldn't. If I had an ionic compound, I'd definitely draw a picture. All right, that's the end of question 1.